Did you know that the speed at which crickets chirp is actually related to the temperature of their surroundings? In fact, about 100 years ago, a guy named Amos Dolbear came up with something that would later become known as Dolbear's Law, which says that there's a relationship between the temperature in degrees Fahrenheit and the number of chirps per minute for different types of species of crickets. For the field cricket, which is the cricket we're most familiar with, this relationship is what's shown on the screen here. So the number of chirps per minute as a function of the temperature in degrees Fahrenheit is equal to 4 times the temperature minus 40. In other words, if I take the temperature in degrees Fahrenheit, subtract 40, and multiply that by 4, I should get the number of chirps per minute. The problem is the thermometer that we have only reads in degrees Celsius. So what are we going to do? Well, one solution is to convert the Celsius temperature to Fahrenheit and then plug that answer into the chirp rate function. So we start with the temperature in degrees Celsius, as you see on the screen. We apply the formula for converting Celsius into Fahrenheit, which is 9/5 times the Celsius temperature plus 32. And then we'll take that answer and plug it into our formula. Well, one other possible solution would be to plug the entire Celsius to Fahrenheit conversion formula directly into the chirp rate function. So the original chirp rate function is shown below using the Fahrenheit temperature. But let's replace the Fahrenheit temperature with the formula that uses the Celsius temperature. So on the left you see what we call the composition of the two functions, and on the right is the actual function that results. On the right, when we do the simplification, we get a formula, 36/5 times the temperature in Celsius minus 32, that gives us the chirp rate now using temperature in degrees Celsius. So when we've dealt with functions in the past, basically what we do is we plug a number into the function in place of the variable. So for example, let's take Dolbear's law and look at it as a function of x. F of x equals 4 times x minus 40. Suppose we have a temperature of x equals 77. So we'll plug 77 in place of x on both sides, as you see. On the right side, we're going to take 77 minus 40, which is 37, and then we'll multiply 37 by 4 to get 148. 148 is the number of chirps per minute for this cricket at 77 degrees Fahrenheit. Now, when we do this with composite functions, what we're doing is actually plugging a function into a function in place of the variable. So in other words, if we start with Dolbear's law, f of x equals 4 times x minus 40, and we have another function which is our conversion from degrees Celsius to degrees Fahrenheit, g of x is 9/5 x plus 32. What we're going to do is plug g into f in place of x. So on the left of this expression, you see f of g of x. And all that means is that g of x is now the input to f. So on the right side, we can expand g of x out into its expression and see f of 9/5 x plus 32. All this means is that we're substituting our variable x in the original function with an expression g of x. Once we do that, we get 4 times, instead of x minus 40, we have g of x minus 40. So 9/5 x plus 32 minus 40, that simplifies to this expression, which finally simplifies to the expression that we had on the previous screen. So working with composition of functions is pretty much just working with function notation. Whatever is in the parentheses becomes the input to the function, whether that's a number or a letter variable or an entirely other function expression. In the next video, we'll take a look at a few examples and see how this actually works.